3 Atlas is growing brighter, and scientists have already detected real changes. This statement is not a trick to grab attention. It is the starting point for understanding what happens when a visitor not born in our solar system approaches the sun and responds to its energy. What we are witnessing is not magic nor a mysterious anomaly. It is physics in action, the same physics that has guided comets and asteroids for billions of years, but now applied to an object whose history began around another star. In recent observations, different teams recorded increases in brightness that align with what is expected when volatile ices begin to sublimate, releasing gas and dust that create a diffuse atmosphere called a coma. This material reflects sunlight, and if the activity continues, it ends up forming a tail. There are no magnetic shields activating, no hidden technology, no shortcuts. There are molecules heating up, dust grains pushed by radiation, jets emerging from active areas, and dynamics that can be measured with precise photometry. What is interesting is not just that it is brighter but how quickly it changes, how it changes, and what this reveals about its composition. Every small jump in luminosity tells a part of its biography. What ices does it contain? How much active surface area does it have? Does the heat open new or constrained cracks? And all of this matters because 3I Atlas could be a natural capsule from another stellar neighborhood, a messenger crossing space with chemical and physical clues about how worlds beyond our sun form and evolve. Before going into details, let us establish the context clearly and calmly because words matter. Saying that 3 Atlas is growing brighter describes a measurable phenomenon, the increase in its apparent magnitude as it approaches the sun and its ices receive more energy. Saying that real changes have already been detected means we are not talking about rumors, but about observed variations that can be compared night after night with photometric standards and light curves. These measurements, made by networks of professional and advanced amateur telescopes, allow for tracing the evolution of the activity, estimating how much matter it is ejecting, and modeling the extent of the coma. If the trend continues, its morphology may reveal more active regions, asymmetries, or the appearance of a well-defined tail. None of this implies impossible behaviors. An interstellar object can act, in physical terms, like a long-period comet. The key difference is its origin. Its hyperbolic velocity and trajectory tell us it is not gravitationally bound to the sun and that it arrived from interstellar space. That fact alone makes it an extraordinary scientific opportunity. Before we delve into the sudden increase in brightness of 3I Atlas and its coincidence with the largest solar flare in decades, there are 3 things you need to do right now to engage the scientific community. First, please like this video to bring this discovery to more observers. Second, subscribe and turn on notifications to receive the latest updates on the real-time tracking. And third, go down to the comments section now and write Cosmos to join the global registry of those following this historic event. Please do this now. Let us be clear about what is confirmed versus what is merely suspected. 3I Atlas is the designation an object identified as the third observed interstellar visitor in the solar neighborhood would receive, after Oumuamua and 2I Borisov. The 3I indicates its hypothetical interstellar nature, while Atlas refers to the search system that first reported it, an automated network that scans the sky to find moving bodies. Unlike familiar comets that return periodically, an object with a hyperbolic trajectory is not bound by the sun's gravity. It arrives from outside, crosses the plane of the planets, and leaves. The confirmation of this interstellar character does not depend on flashy labels, but on orbital parameters, an eccentricity greater than 1, positive orbital energy, and a velocity at infinity that cannot be explained by local interactions. That is to say, its very motion tells us it comes from another region of the galaxy. That origin is relevant, but it is not enough to explain the increase in brightness. The apparent luminosity of a small, dark object depends on several variables. Its distance from the sun, its distance from Earth, the phase angle, the geometry of sun-object observer, its effective size, its albedo, and crucially for cometary bodies, its activity. When an ice-rich nucleus heats up, those ices sublimate and generate a gaseous envelope that traps and carries dust. The resulting coma scatters sunlight and can increase the apparent magnitude even if the nucleus is modest. In short, an initially faint object can brighten optically as it begins to lose material. What makes 3I Atlas interesting is not that it is magically getting brighter, but that the pattern of its brightness can reveal the physics of its surface. If the increase follows a smooth curve as its distance to the sun decreases, that suggests sublimation controlled by the temperature of common ices like carbon dioxide or water in appropriate ranges. If, on the other hand, sudden jumps appear that could indicate the opening of new fractures, the release of fresh patches, or outburst events where an internal cavity depressurizes and ejects gas and dust all at once. Astronomers discriminate between these possibilities with repeated photometry and thermophysical models of the nucleus. Now, since 3I Atlas does not share the same history as comets from our Oort cloud, every piece of data about its activity becomes a clue about its origin. The ratio between gas and dust can hint at which ices dominate or the size of the released grains. Asymmetries in the coma, when observable, can arise from the nucleus's rotation and the location of active spots at specific latitudes. The rotation in turn can be measured indirectly from small periodic modulations in brightness or, with sufficient resolution, by tracking jets that appear to rotate over time. None of this requires extraordinary assumptions. They are the same tools we use to understand traditional passing comets, only now applied to an external messenger. The importance of brightness is also connected to the possibility of seeing the object with modest instruments. Although most measurements useful for science come from telescopes equipped with calibrated CCD cameras, the overall changes in magnitude determine whether an advanced amateur can record it from a dark sky or whether the general public might eventually perceive it with the naked eye. It is honest to say that without specific daily data, visibility to the naked eye is not promised. However, documenting that it is growing brighter describes a trend consistent with solar approach and cometary activity. The beauty of this process lies in the fact that anyone with discipline can follow it. One takes an image, compares it with reference stars, builds a light curve, and verifies if the increase exceeds the geometric expectation from the change in distance. A point that often causes confusion is the word acceleration. In orbital dynamics, all bodies accelerate due to the sun's gravity. What usually draws attention in active comets are non-gravitational accelerations, small deviations in their trajectory due to gas jets acting like tiny rockets. This is not extraordinary or impossible. It is a well-known term in orbital models. If 3 Atlas shows sufficient activity, it is reasonable to expect an adjustment in its orbital solution that incorporates a non-gravitational parameter. Teams that publish ephemerides include these terms when there is robust data. Using that word responsibly avoids misunderstandings that open the door to stories not supported by measurements. Another element worth emphasizing is the role of light scattering and radiation pressure. Finer dust grains are pushed more effectively and form subtle structures. Sometimes, dust tails and ion tails are observed, the latter composed of charged particles interacting with the solar wind. The appearance, shape, and orientation of these tails provide clues about grain size, emission rate, and the heliospheric environment. If 3I Atlas develops a clear tail, its geometry will be a natural laboratory for that physics. Again, there is no need for embellishment. The interaction between radiation, particles, and ejected material is enough to create spectacular and completely explainable images. Finally, recognizing that 3 Atlas is under international scrutiny helps separate noise from signal. Observation networks cross-check data, compare magnitudes between filters, eliminate atmospheric biases, and publish results with explicit uncertainties. Science progresses precisely in this way, by measuring, verifying, and measuring again. The increase in brightness communicated with that rigor is not a cry of alarm nor a miracle. It is the natural evolution of an icy body entering a hotter region of space. If Oumuamua and Borisov taught us anything, it is that interstellar visitors can surprise, but their surprises are best understood with patience and with models that respect physical laws. 3 Atlas does not need to be fantastic to be fascinating. It is enough to observe it well. From the moment it was first detected, one of the main objectives was to define the trajectory of 3I Atlas with precision. To achieve this, multiple observations were compiled from different observatories around the world, measuring its position night after night against known reference stars and using this data to calculate a preliminary orbit. The computational programs that perform this work take into account the gravity of the Sun, the major planets, and if the object's activity warrants it, even non-gravitational forces generated by gases escaping its surface. The first calculations indicated its orbit was hyperbolic with an eccentricity greater than 1, which implies the object is not gravitationally bound to the Sun and will eventually leave the solar system after its passage. Over time and with new, more precise measurements, that orbit was refined. At this moment, the most reliable data describe 3I Atlas as approaching perihelion, that is, the closest point it will have to the Sun in its entire trajectory. Its velocity increases naturally due to solar gravitational attraction, which is completely expected according to Kepler's laws and Newtonian dynamics. As it approaches, its distance to Earth also decreases, although it will not pass dangerously close to our planet. The ephemerides published by NASA's JPL specify approximate dates, position in celestial coordinates, estimated magnitude and rates of change, which allows professional and amateur astronomers to plan observations with sufficient anticipation. At this point, it is important to clarify that when it is said to be accelerating, this does not refer to a strange or inexplicable phenomenon. All objects falling towards the Sun accelerate because gravity increases as distance decreases. The correct term would be that it is increasing its orbital velocity as a result of a very open elliptical or hyperbolic trajectory. What could be surprising, though it has not yet been definitively confirmed, is if small deviations in that orbit due to non-gravitational forces are detected. This has already happened with other comets like 1P/Halley or C/1995-01 Hale-Bopp, and it is due to jets of gas escaping from the nucleus slightly pushing the body. But in all cases, these effects are explained by applying conventional physics without the need for extraordinary ideas. So far, the measurements indicate that 3I Atlas follows a trajectory stable and coherent with its provisional classification as an interstellar object. Its velocity, interactions with the solar gravitational field, and future projection align with robust mathematical models. The scientific interest focuses on measuring its position and brightness with the greatest possible precision to see if small deviations will appear as it gets closer to the Sun and its activity increases. These variations refine the orbital parameters and help confirm with greater certainty its origin external to the solar system. For an object to officially receive the designation 3I, it must be demonstrated that its trajectory cannot be explained by a previous interaction with planets or by an extreme orbit bound to the Oort cloud. That confirmation comes solely from data, not assumptions. The exact position of 3I Atlas in the sky changes every night relative to the background constellations. In astronomical coordinates, it is expressed via right ascension and declination. These coordinates are updated frequently because the object moves noticeably even over a few days. To observe it, astronomers use precise stellar catalogs like Gaia DR3 and software tools like Stellarium, Sky Safari, or Carte du Ciel, where they can input the orbital data published by the Minor Planet Center or JPL Horizons and simulate its location in real time. This precision is crucial because its brightness is still far below the naked eye visibility limit, so it is necessary to point telescopes exactly to find it among millions of stars. When its trajectory is projected forward, key dates can be determined: the moment of perihelion, the minimum distance to the Sun, the closest approach to Earth, and when it might reach its maximum apparent brightness. These projections change slightly with each orbital refinement but serve as a general guide. For now, calculations indicate there will be no risk to our planet. Its passage will be distant and fast, as befits an interstellar visitor. After reaching perihelion, it will begin to move away, its activity will decrease as it loses solar heat, and eventually it will become too faint to detect. However, during the interval close to perihelion, the most drastic changes occur. Increase in brightness, more evident formation of a coma or tail, and potential fractures on the surface if heating causes mechanical stress. It is important to note that the brightness observed from Earth does not depend solely on its distance from the Sun, but also on its distance from our planet, its orientation relative to sunlight phase angle, and whether there is activity from the amount of ejected material. An object can be closer to the Sun but farther from Earth, which would make its apparent brightness not increase as much as expected, or conversely, it can be relatively far from the Sun but approaching Earth, which momentarily makes it more visible. These factors are carefully calculated when trying to predict if the object will be visible with binoculars, small telescopes, or even to the naked eye. For 3I Atlas, current estimates suggest it could become observable for amateur telescopes if the activity increases sufficiently, but it is still too early to be sure. Each measurement of its position allows for adjusting the orbital parameters with greater accuracy. This is achieved through the least squares method, which reduces the differences between the calculated orbit and the real observations. Over time, the margin of error decreases and the trajectory becomes almost definitive. In the case of 3I Atlas, this process continues, and it is likely that astronomical agencies will publish frequent updates as we approach perihelion. These updates interest not only the scientific community but also orbital dynamics simulators, educators, and the general public who wish to know the destiny of this cosmic visitor. In summary, 3I Atlas follows a trajectory that takes it towards a significant approach to the Sun. Its velocity increases as a natural result of gravity, and its brightness intensifies due to heating and potential cometary activity. There are no signs of impossible behaviors, mysterious accelerations, or artificial structures. What we have is a real object governed by known physical laws, offering us an exceptional opportunity to study matter that may have formed around another star millions or billions of years ago. Its passage is brief, but every piece of data obtained now could reveal entire chapters of how the galaxy works beyond our neighborhood. The increase in brightness of 3I Atlas is not a mysterious phenomenon. It is a direct consequence of solar heating and the physical processes that affect icy bodies when they approach an intense source of energy. Every comet or active asteroid undergoes a gradual transformation as it reduces its distance to the Sun. Ices that remain stable in the cold of deep space begin to sublimate, that is, transition from solid to gas without melting. First, this change releases gases that carry dust particles from the nucleus and form a diffuse envelope called a coma. This cloud scatters sunlight in all directions, increasing the object's apparent luminosity and creating the impression that it is shining brighter. In reality, the nucleus still reflects the same amount of light according to its size and albedo, but the coma multiplies the optical scattering area and dominates the total brightness. When the apparent magnitude of 3I Atlas is measured and compared with previous dates, astronomers observe variations consistent with this mechanism. The upward trend coincides with the reduction of its heliocentric distance, which means the progressive heating is activating regions on its surface. It is likely the nucleus is composed of a mixture of water ices, carbon dioxide, carbon monoxide, and other volatile compounds common in comets, although its exact proportion is still unknown. If it comes from another stellar system, the chemical differences could be small or notable, but only spectroscopy will be able to confirm this. So far, the spectral signature detected from ground-based telescopes shows bands compatible with typical comet molecules, which reinforces the interpretation that the brightness comes from natural activity and not exotic phenomena. The sublimation process does not occur uniformly over the entire surface. Sunlight falls more directly on some zones depending on the tilt of the rotation axis and the irregular shape of the nucleus. These differences cause certain sectors to heat up first, generating localized jets that escape at high velocity. Each jet acts as a small source of gas and dust, creating asymmetric patterns in the coma. If observed carefully, these asymmetries produce temporary variations in brightness that can repeat periodically, reflecting the nucleus's rotation. Determining this rotation period is one of the current goals because it helps understand the object's internal structure and mechanical stability. A body with fast rotation can fragment if centrifugal forces exceed the material's cohesion, while one with slow rotation can maintain its integrity throughout the passage through perihelion. As the heat penetrates deeper layers, gases trapped in pores or cracks find an exit and increase the internal pressure. This pressure can enlarge pre-existing fractures or open new ones, exposing fresh material that was previously protected from the sun. When this occurs, the brightness can increase abruptly, a phenomenon known as an outburst. Such events have been documented in numerous comets and represent episodes of intense, short-lived activity. If an outburst were detected in 3I Atlas, it would be an indicator of structural changes in the nucleus, but it would not mean something outside of known physics. In fact, these outbursts are valuable opportunities to analyze the composition of the newly exposed material, as the reflected light and spectral emissions can reveal the presence of compounds that normally remain hidden. The telescopes monitoring 3I Atlas employ differential photometry techniques to quantify these brightness increases. Instead of measuring absolute luminosity, they compare the object's flux with that of stars of known magnitude in the same image. This compensates for atmospheric effects and instrumental variations. By repeating these measurements on different nights, a light curve is built that shows the evolution of the activity. The values are corrected for distance to the Sun and Earth, so one can distinguish if the increase is due to geometric factors or a genuine increase in gas and dust production. In the case of 3I Atlas, the slope of this curve has been steeper than what would be expected from solar approach alone, which confirms that the activity is intensifying. Intensification does not necessarily imply a sudden change in its nature, but a progressive response to the environment. As solar radiation heats the surface, the most volatile ices sublimate first, followed by less volatile ones that require more energy. This sequence creates layers of activity that migrate towards increasingly deeper regions. At some point, when the gas flow diminishes, the coma reduces and the brightness decays. The complete cycle describes the active life of a comet during its close passage to the Sun. For an interstellar visitor like 3I Atlas, this could be its first and only encounter with a star in millions of years, so the loss of material can significantly alter its mass and shape before it returns to interstellar space. Another reason for the brightness increase is forward scattering, an optical effect that occurs when the angle between the sun, the object, and the observer approaches zero. Under these conditions, dust particles reflect more light towards the observer's direction, temporarily increasing the apparent luminosity. Astronomers correct for this effect in their models, but for the public, it can translate into a sudden brightening when it is actually a predictable geometric phenomenon. Knowing how to distinguish between a physical change and a geometric one is an essential part of scientific analysis. 3i Atlas offers an excellent opportunity to apply these corrections and compare results between different teams, strengthening the international collaboration that characterizes modern astronomy. Besides visible brightness, other wavelengths are analyzed, such as infrared and ultraviolet. In the infrared, one can measure the surface temperature and sublimation rate, while in the ultraviolet, specific emissions from molecules like OH, CO, or CN are detected. Each spectral band provides complementary information and helps build a more complete model of the object's thermal and chemical behavior. The combined data show that the increase in activity coincides with the sublimation models expected for an icy body passing within a few astronomical units of the Sun. There are no indications of unnatural processes or unknown mechanisms. The fascinating thing is that known physics is sufficient to explain the evolution of the brightness in great detail. The media interest around 3 Atlas is due in part to the rarity of finding an object that comes from another star. The idea that an interstellar visitor reacts to the heat of our Sun sparks curiosity because, in a way, it is an exchange between stellar systems. Every grain of dust released carries the chemical signature of its place of origin, and studying it allows for comparing the ingredients of planetary formation in different parts of the galaxy. If high-resolution spectra can be obtained, we could learn if interstellar ices contain different proportions of carbon, oxygen, or nitrogen compared to local comets. In that context, the brightness increase is not just a visual spectacle, but a window into the chemistry of other worlds. In simple terms, 3i Atlas is growing brighter because it is waking up. Solar heat activates its surface, gases emerge, dust rises, and light scatters. Everything fits with the laws of thermodynamics, fluid dynamics, and optics. Every reflected photon is a story about temperature, pressure, and composition. Observing its evolution is observing physics functioning in real time on an astronomical scale. And every measurement, every image, every piece of data compared with the models confirms that science can describe the beauty of the universe without needing to adorn it with inventions. When it is stated that scientists have detected real changes in 3i Atlas, it is not about a visual impression or a subjective interpretation. It is the result of a rigorous procedure involving repeated observations, instrumental calibration, data comparison, and statistical analysis to verify that the increase in brightness, the expansion of the coma, or any apparent modification is not due to measurement failures, atmospheric conditions, or human error. Modern astronomy is based on precision and reproducibility, so every record must be able to be validated by other independent observatories, using the same stellar references and the same photometric methods. It all begins with obtaining images of the object using telescopes equipped with high-sensitivity CCD or CMOS sensors. These cameras capture the light from the comet and the nearby stars in the field of view. Since the goal is to measure how much light the object emits or reflects and compare it with previous nights, it is essential to eliminate any external factor that could alter the measurement. Therefore, before analyzing the data, effects like the sensor's electronic noise, variations in the detector's temperature, darkening towards the edges of the field of view, called vignetting, and distortions caused by the atmosphere are corrected. These corrections are performed through standard procedures like dark frames, bias frames, and flat fields, which allow for cleaning the image and leaving only the useful astronomical signal. Once the image has been corrected, astronomers use differential photometry to determine the object's relative brightness. This involves selecting reference stars within the same image, whose brightness is already well cataloged in databases like the Gaia catalog. By comparing the luminous intensity of the comet with that of these stars, it is possible to calculate its apparent magnitude with great precision. If the measurement is repeated many times on different days, a light curve can be built that shows how the brightness changes over time. For 3i Atlas, these curves have revealed a consistent increase in luminosity as it approaches the Sun, which coincides with the onset of cometary activity. It is not a simple visual coincidence, but a measurable pattern that exceeds the margins of error. Besides the total brightness, the morphology of the coma is analyzed. This is done by examining the light profile around the nucleus, that is, how the intensity decreases as we move away from the center. In an inactive object, the profile is very concentrated, similar to a defocused star, but when there is gas and dust emission, the profile widens, forming a detectable nebulosity. By comparing images from different nights, one can measure if the coma has expanded, if there are brighter regions, or if asymmetric structures appear that could indicate gas jets. In the case of 3I Atlas, several observers have reported a slight expansion of the coma and an increase in its angular diameter, which reinforces the evidence that the object is experiencing real physical activity. Another method used to confirm changes is spectroscopy. This technique consists of decomposing the object's light into its wavelengths to identify which elements or molecules are present. If water ice sublimates, the vapor can be dissociated by solar radiation, producing OH radicals that emit in the ultraviolet. Carbon monoxide, CO, and carbon dioxide, CO2, also have specific signatures in the near-infrared. Detecting these spectral lines confirms that the additional brightness does not come only from the reflection of sunlight on the nucleus, but from gases released by activity. Although the spectroscopic data for 3I Atlas are still limited, some preliminary reports suggest the presence of typical comet molecules, which agrees with the observed brightness increase. One of the most important parts of confirming that these changes are real involves comparing data from different observatories around the world. It is not enough for one telescope to detect a brightness increase. It is necessary for other teams, using their own instruments and methods, to observe a similar result within acceptable error margins. When that happens, one can confidently state that the phenomenon is objective and not the product of an instrumental or processing error. In the case of 3 Atlas, coincidences have already been reported in data from professional observatories and advanced amateurs, which strengthens the conclusion that its activity has genuinely increased. Another piece of evidence comes from the official ephemerides published by centers like the Minor Planet Center and the JPL. These organizations incorporate the observed positions of the object into their calculations and adjust its orbit using mathematical models. If the comet's activity generates non-gravitational forces, this will be reflected in small deviations from the expected trajectory. So far, no significant deviations have been detected in the case of 3I Atlas, but astronomers continue to monitor it closely because if its activity increases, it could begin to show these small perturbations. Should this occur, it would be another measurable indication that the comet is actively expelling gas and slightly modifying its trajectory. It is important to emphasize that this entire process is carried out with caution and without hasty conclusions. Astronomy requires patience and data repetition to verify any claim. That is why, when it is said that 3I Atlas is brighter and that real changes have been detected, it refers to the fact that current measurements show a consistent and verifiable trend. No one claims that something unnatural is happening. On the contrary, the typical behavior of an icy body awakening as it enters a warmer region of the solar system is being observed. This is precisely the reason why studying it is so valuable, because it represents a unique opportunity to observe how interstellar material reacts to the Sun. Every new image, every light curve, every recorded spectrum adds pieces to the puzzle. What is an ascending brightness curve today might show a pause or a decline tomorrow if the nucleus depletes its most volatile reserves, or perhaps it will have a sharp peak if an outburst occurs. None of these possibilities require imagining hidden technologies or mysterious phenomena. It is about physics, chemistry, solar energy, and natural laws. And that, far from diminishing its interest, makes it an authentic phenomenon that connects us with the reality of the universe, a universe that does not need to be exaggerated to be astonishing. Every time an object like 3I Atlas approaches the Sun, its velocity increases. This is not something strange or new. It is a direct consequence of solar gravity accelerating every body that approaches it, just as an object falls faster when it nears the ground on Earth. Newton's law of universal gravitation and Kepler's laws explain that as the distance between an object and the Sun decreases, the orbital velocity increases naturally. Therefore, saying that 3I Atlas is accelerating does not at all imply that something anomalous is occurring or that extraordinary explanations are needed. It simply means it is responding to the Sun's gravitational force like any comet or asteroid in orbit. What truly interests astronomers is not whether it accelerates because that is expected, but whether there is some type of additional acceleration that cannot be explained by solar gravity alone. That extra acceleration, if it were to be detected, would be called non-gravitational acceleration. And far from being something mysterious, it has a very well-known explanation: cometary activity. When the ices in the nucleus sublimate and emit gas, that gas exits at high velocity in the form of jets that slightly push the nucleus in the opposite direction, like tiny natural engines. This type of thrust, although small, can slightly modify the object's orbit over time. This has already been observed in comets like 1P/Halley, 67P/Churyumov-Gerasimenko, visited by the Rosetta probe, and also in long-period comets. Therefore, if something like that were detected in 3I Atlas, it would be interesting but not unexpected or outside the known laws of physics. To determine if non-gravitational acceleration exists for 3I Atlas, astronomers compare the object's real position with the position it would have if only the gravity of the Sun and planets acted upon it. This is done by calculating ephemerides with mathematical models. If, when comparing real observations with these predictions, the object appears a bit ahead or behind the expected position, and that difference cannot be explained by measurement errors, then one can infer that an additional force is acting. This deviation is described through non-gravitational parameters within the orbital solution. It is a complex mathematical procedure that requires a lot of positional data recorded on different days, taken from various observatories, and under careful conditions. Up to this moment, no significant non-gravitational acceleration has been reported for 3I Atlas. This does not mean it does not have any, but rather that if it exists, it is still very small or the data are not sufficient to confirm it reliably. It is important to differentiate this from other cases like Oumuamua, the first interstellar object detected in 2017. In that case, a small but real non-gravitational acceleration was observed. That acceleration generated debate among scientists about its cause. Some proposed it was the result of the release of trapped molecular hydrogen from ice. Others suggested the effect of solar radiation pressure on a very flat shape, and some media exaggerated with ideas about artificial technology. However, subsequent research has shown that this behavior could have been due to natural processes, especially the release of gases difficult to detect. The relevant point here is that non-gravitational accelerations exist, have been measured in other objects, and have coherent physical explanations. In the case of 3I Atlas, astronomers are attentive to this type of behavior. If its cometary activity increases, it is possible it might start to show a measurable deviation in its trajectory. But to date, no solid evidence of a significant deviation from its pure gravitational orbit has been published. Therefore, claiming that it has accelerated in an impossible way or that it changed its velocity mysteriously is neither correct nor supported by scientific data. What can be stated, without exaggeration, is that its velocity is increasing as it approaches the Sun and that this is totally normal and predicted by orbital dynamics. To measure the real velocity of objects like 3I Atlas, the Doppler method is used through spectroscopy. When an object moves towards Earth, the spectral lines of the reflected light shift slightly towards the blue. If it moves away, they shift towards the red. By measuring that tiny variation, astronomers can deduce the radial velocity. Complemented with data on angular position in the sky, a three-dimensional model of its motion is obtained. These data, combined with numerical integrations of orbits, confirm that 3I Atlas is behaving exactly as expected. It increases its velocity following known physical laws without inexplicable jumps. So, why do headlines appear talking about impossible acceleration or behaviors that defy science? Because many people mix the term natural acceleration with insinuations of extraordinary events without understanding its real meaning. In science, acceleration is not something rare. It is a mathematical description of how velocity changes over time. Saying that 3I Atlas accelerates is not equivalent to saying something abnormal is happening. The abnormal thing would be if it did not accelerate as it approached the Sun. What is truly important is not whether it accelerates, but whether it accelerates more or less than what gravitational models predict. So far, what the observations show is coherent. The increase in brightness is due to cometary activity. The velocity increases due to solar gravity, and its orbit fits within a typical hyperbolic trajectory for an interstellar object. Agencies like NASA's JPL and the Minor Planet Center continue updating their databases with positions, magnitudes, and observation dates. Each new measurement allows for refining the orbit further, reducing the margins of error, and in case non-gravitational forces appear, detecting them rigorously. The study of 3I Atlas continues to advance. It is possible that in the coming weeks or months, small variations in its orbit due to gas jets will be detected, or perhaps not. In either case, the explanation will lie within the framework of well-known physics. Therefore, the true fascination lies not in expecting the impossible, but in understanding the real. A body that comes from another place in the galaxy, that heats up for the first time in a long while, that releases its frozen layers into space, and that allows us to study how interstellar matter behaves upon entering the Sun's domain? Every time a new object is discovered in the solar system, especially if it comes from interstellar space as suspected with 3I Atlas, the same question arises on social media and sensationalist media. Could it collide with Earth? To answer this scientifically and clearly, the first thing calculated after discovering an object is its trajectory. This trajectory is determined by comparing many observations of the object on different nights, measuring its position relative to fixed stars, and feeding this data into a celestial mechanics program that calculates its orbit around the Sun. In the case of 3I Atlas, from the first days of observation, it was seen that its orbit is not closed like that of planets or periodic comets, but hyperbolic. This means it is not trapped by the Sun's gravity. It comes from outside, will pass through the closest point, perihelion, and afterwards will leave forever back into interstellar space. When an orbit is hyperbolic, it also means the object will not make multiple revolutions nor have frequent encounters with Earth. Once the trajectory is calculated, astronomers can predict with considerable precision what its minimum distance to our planet will be and on what date it will occur. In the case of 3I Atlas, the ephemerides from the Jet Propulsion Laboratory indicate it will pass millions of kilometers from Earth, much farther than the average distance between Earth and the Moon. There is no scenario based on real data in which this object represents a threat. For there to be a possibility of impact, it would have to have an orbit that crosses Earth's at the exact same moment our planet passes through that point. But the orbits do not coincide, and furthermore the object travels very fast, so it cannot be gravitationally captured by Earth. Another important point is that orbits are not calculated just once. They are continually refined with each new observation. Every time a telescope records the object's position relative to reference stars, a new data point is added to the database and its trajectory is recalculated with greater precision. If there were a risk of impact, the error in the prediction would gradually reduce and the minimum distance would approach dangerously. In contrast, with 3I Atlas, the opposite has occurred. Each observation confirms that its path is clearly far from our planet. Even if there were small non-gravitational forces from cometary activity, like gas jets that can slightly alter the motion, these deviations are not large enough to change its orbit into an impact trajectory. However, many people confuse the terms approaches, or passes near the Sun, with passes near Earth. They are completely different things. An object can be millions of kilometers from Earth and at the same time be approaching the Sun. The perihelion has nothing to do with our planet, but with the minimum distance to the Sun. In the case of 3I Atlas, its perihelion will be relatively close to the Sun, which explains why it is growing brighter, but it does not mean it will cross paths with Earth. Its minimum distance to our planet occurs on a different date and from a completely different region of space. This separation between the two events is what provides safety. There is no spatial or temporal coincidence. NASA and other space agencies maintain programs that search for and monitor potentially hazardous objects, near-Earth objects or NEOs. These are bodies whose orbit does cross Earth's and that pass within 0.05 astronomical units, about 7.5 million kilometers. 3I Atlas is not part of that list. It does not meet any of the conditions for a hazardous NEO. Its trajectory does not intersect Earth's. Its velocity is too high to be captured, and it does not even come within the range considered risky. The astronomers studying this object do so for scientific interest because it is possibly interstellar for its behavior and composition, not because it poses a danger. Even if we imagined extreme scenarios like fragmentation of the nucleus or violent ejections of material, it would still not be a risk. The fragmentation of a comet occurs when thermal or rotational forces exceed the material's cohesion. This happened to comet Shoemaker-Levy 9 before it collided with Jupiter in 1994. But for a fragment of 3I Atlas to represent a danger, it would not only have to break apart but also drastically change its orbit to align with Earth at the exact moment. That combination of events is not supported by any observation or current physical model. The forces needed to do this are hundreds of times greater than those a comet's sublimation can generate. It is important to clarify this because often real scientific terms like increase in brightness, activity, non-gravitational acceleration, are mistakenly mixed with ideas of risk or catastrophe. But everything happening with 3I Atlas can be explained with standard physics. There are no signs of unusual trajectories or abrupt changes that call its orbital behavior into question. Every night of observation reinforces the same thing. It is an object that will pass by, will be studied, will increase in brightness for a while, will then fade as it moves away from the sun, and will exit the solar system never to return. Even if its brightness increases much more, or if it develops a spectacular tail, that will not imply danger. In fact, it would be a positive thing because it would allow for better observation and more detailed study of its composition. The more active it is, the more gas and dust it releases, which facilitates analyzing its spectrum, knowing the present compounds and comparing them with comets of local origin. For science, the best scenario is that it shines as much as possible without fragmenting too quickly. For terrestrial safety, as long as its orbit does not cross our planets, the risk level remains at zero. For all these reasons, when it is scientifically stated that 3I Atlas does not represent a danger to Earth, it is not a phrase to calm the public. It is a conclusion backed by precise orbital calculations, updated data, and constant comparison with observatories around the world. Changing that conclusion would require a huge and never-before-seen deviation for an object like this. And if one day the data showed something different, the agencies would communicate it officially, as they have always done with any potentially hazardous body. 3I Atlas is interesting, yes, it is valuable for science, yes, but it is not a threat. When a comet or an active object begins to increase in brightness, the question inevitably arises of whether it will become visible without a telescope. With 3I Atlas, this is exactly what is happening. Many people want to know if they will be able to see it from their home, if it will cross the sky like a bright line, or if it will be just a faint point detectable only with specialized instruments. To answer precisely, it is not enough to say yes or no. One must understand what determines the visibility of an object like this: its distance from the sun, its distance from Earth, its size, the amount of gas and dust it ejects, the angle with sunlight, light pollution, and even the brightness of the moon at the time of observation. Right now, what is known is that 3I Atlas is increasing in brightness as it approaches the sun, and this increase has been confirmed with photometric measurements. However, its current apparent magnitude is still far above the limit visible to the human eye. A telescope, or in some cases large binoculars under a dark sky, is needed to detect it. Astronomers following it have estimated that if the activity continues to increase steadily and if there is no significant fragmentation of the nucleus, it could reach a magnitude sufficient to be seen with small telescopes or even common binoculars. But to reach the point of being visible to the naked eye, its brightness would have to increase by several magnitudes more than what has been observed so far. And although it is not impossible, it is still too early to state this with certainty. When discussing naked eye visibility, the key figure is magnitude 6, which is approximately the limit a human eye can perceive in a completely dark sky, without artificial lights and with good eyesight. For a comet or an object like 3I Atlas to be seen without instruments, it must surpass that threshold. Some comets like Hale-Bopp in 1997 or Neowise in 2020 managed to shine much brighter, reaching magnitudes of 0 or even negative, but they had special conditions: large nuclei, enormous amounts of ejected material, and close distances to Earth. In the case of 3I Atlas, although its brightness is increasing, it is not clear if the activity rate will be high enough to reach that level of visibility. One must also remember that this object will not pass extremely close to Earth. Its minimum distance will be much greater than that of comets that have been spectacular in the past. Even if its perihelion heats it enough to generate a coma and a tail visible with telescopes, its position in the sky may not be favorable for casual observers. Visibility depends not only on brightness but also on its height above the horizon, the time, and the direction in which it would appear. If the object is very low on the horizon or too close to the sun in the sky, even a relatively bright comet could be difficult to detect. Astronomers use models that predict an object's future brightness based on its past behavior and its distance from the sun. Currently, these models for 3I Atlas show an ascending brightness curve, but with significant uncertainty. Some optimistic scenarios suggest it could reach magnitude 7 or 8, sufficient for binoculars from dark zones. Other more conservative models indicate it might remain at magnitude 10 or fainter, which would require medium-sized telescopes. So far, none of the serious scientific models project that it will reach negative magnitudes or that it will be a spectacular comet visible in cities with the naked eye. There are no data indicating it will be as bright as Neowise or Hale-Bopp. It is important to understand that comet behavior can be unpredictable. Some fragment suddenly and become brighter for a few days. Others disintegrate completely before perihelion, fading forever. That is why astronomers prefer to talk about probabilities, not certainties. In the case of 3I Atlas, the responsible thing is to say that its brightness is increasing, that it does show confirmed activity, but that it is still not possible to state it will be visible to the naked eye. The most likely scenario, if it maintains its current behavior, is that it will become observable with small telescopes and maybe with binoculars, but not with the naked eye from urban areas. For the public, the best approach is to follow the official reports from the Minor Planet Center, the JPL, and reliable professional or amateur observatories. They update the observed magnitude, the object's position in the sky, and the most favorable dates for attempting to see it. Anyone wanting to try to observe it needs a dark sky, far from artificial lights. Programs like Stellarium allow loading the object's orbit and indicating exactly its position in the sky from any location in the world, on any date and time. This way one does not have to guess, the observation can be planned with precision. In summary, 3i Atlas is growing brighter, but it is still not visible without instruments. One cannot rule out that it will increase much more. But neither can it be promised. For now, the scientific evidence says that there is real activity, that the brightness is rising, that the object is responding to solar energy, but the possibility of seeing it with the naked eye remains uncertain. We will have to wait for the weeks close to its perihelion to know if it becomes a notable object or if it will only be appreciated by telescopes. What is happening with 3i Atlas is not the end of its story, but the beginning of the scientifically most interesting stage, the closest approach to the Sun. Now that the object has shown a real increase in brightness and confirmed signs of cometary activity, astronomers from different countries are preparing to record what will happen when the solar heat reaches its most intense point on its surface. The question is not only how much brighter it will get, but whether its behavior will remain stable or if it will enter a more violent phase where its nucleus could fragment, release large amounts of material, or even fade abruptly if it quickly loses its ice reserves. In the coming weeks, as its heliocentric distance decreases, the energy it receives from the Sun will increase exponentially. This increase will produce more sublimation of volatile compounds, that is, gases released directly from the ice into space, and these gases will carry a greater amount of dust. In astronomical terms, the coma is expected to become denser, to expand, and for the pressure of the solar wind to form a more defined tail. The direction of the tail does not depend on the object's trajectory, but on the constant flow of charged particles coming from the Sun that push the fine dust to the opposite side. If the activity increases enough, scientists hope to observe not only a dust tail but perhaps also a finer, straighter ionic tail, generated by ionized molecules. This double structure is common in active comets and is one of the clearest indicators of the interaction between solar radiation, gas, and charged particles. But although this is the most logical expectation according to known physical laws, one cannot rule out unexpected events. No one knows how much internal pressure the pores of the nucleus have, nor if it contains cavities with trapped gases. If the heat penetrates deep layers and releases pressures accumulated over millions of years, an outburst could occur, in which an enormous amount of gas and dust is expelled in a few hours. This would cause an abrupt increase in brightness and momentarily alter the coma. It could even slightly modify the nucleus's rotation, since the jets exiting with force act like small thrusters pushing in one direction. This would not be something unnatural, but a phenomenon known in comets like 17P/Holmes or 29P/Schwarzmann, Watchman. If something similar occurs with 3i Atlas, it would be an excellent opportunity to study fresh material from the interior of the nucleus. Another possibility scientists consider is fragmentation. When a comet heats up too much, it can break apart due to thermal stresses, centrifugal forces if it rotates fast, or the expansion of internal gases. Some comets split into several fragments that follow similar trajectories but with small deviations. If 3i Atlas comes from interstellar space, its internal structure could be more fragile than that of comets that have passed repeatedly near the Sun. This would make it more susceptible to breaking apart. If that occurs, telescopes would detect new condensations within the coma with secondary fragments losing material. Fragmenting would not imply danger for Earth, but it would change its brightness and modify the flow of gas and dust. For now, there is no proof of fragmentation, but it is something that is closely monitored. What is certain is that the brightness will continue to be monitored every possible day. The light curve, the graph showing how its magnitude changes over time, will be a fundamental tool. If that curve continues to increase smoothly, it will be a sign of progressive and stable sublimation. If it suddenly flattens or decreases, it could indicate that part of the surface stopped releasing gas or that the nucleus lost its most volatile layer. And if it shoots up sharply, it would be a sign of an explosive event. All of this will be known through real data, not assumptions. Besides brightness, scientists will pay attention to the shape of the coma. With long-exposure images, one can analyze if there are fan-shaped structures, if the jets follow repetitive patterns that reveal the nucleus's rotation, or if waves appear indicating rapid changes. High-resolution images from the Very Large Telescope in Chile, the Subaru in Hawaii, and the future Vera Rubin telescope may allow separating the nucleus from the diffuse brightness surrounding it to measure its size, albedo, and rotation period with greater accuracy. There is also interest in studying its spectrum. As it gets closer to the Sun, more intense spectral lines will appear, especially from OH, a result of water photodissociation, cyanide, carbon monoxide, and carbon dioxide. Comparing these lines with those of other comets will allow determining if the chemistry of 3I Atlas matches that of comets from the Oort cloud or if it has different proportions of carbon, oxygen, nitrogen, or complex organic molecules. If clear differences are detected, it would be direct evidence that it formed in a stellar system with chemical conditions different from ours. Another aspect that could be studied is the evolution of its tail as it passes through perihelion and then moves away. When a comet moves away from the Sun, its activity decreases. The tail weakens, the coma contracts, and the brightness falls. If 3I Atlas survives perihelion without breaking apart, scientists will be able to study how its activity gradually shuts down. This is also valuable because it allows calculating its mass loss rate and estimating how much material it will retain when it returns to interstellar space. In other words, how much of the original comet will survive. There are also open questions about its rotation. If the nucleus rotates slowly, heating can concentrate on one side and produce very defined active zones. If it rotates fast, the heat is distributed more evenly, but structural tension also increases. If the rotation is extremely fast, it could even disintegrate due to centrifugal forces. Measuring its exact rotation is not easy, but it can be deduced by observing small periodic brightness variations or the movement of structures within the coma recorded over several nights. The only thing not expected, because there is no data supporting it, is the appearance of impossible phenomena like artificial magnetic shields, inexplicable accelerations, or behaviors that contradict physical laws. Everything observed so far fits the physics of active comets, the behavior of sublimating ice, and the effect of solar radiation. Science does not need to invent. It only needs to observe patiently and measure precisely. So, in summary, scientists expect more brightness, more activity, possible tail formation, perhaps outbursts, maybe fragmentation, and above all, a huge amount of data to understand how an interstellar object reacts to the Sun. What comes next will depend on what nature decides to show, but it will be completely within the realm of science. The brightness of an object like 3I Atlas is not merely a visual spectacle. It is a message encoded in light that reveals what it is made of, how it is reacting to solar heat, and what history it might have had before entering our solar system. In astronomy, brightness is not interpreted as a simple increase in light, but as a combination of physical phenomena: sublimation of ices, scattering of dust, emission of gases, solar reflection, and the geometry between the Sun, the object, and the observer. Analyzing how that brightness changes, at what rhythm, and with what characteristics allows scientists to deduce its composition, the size of its particles, the chemistry of its surface, and even clues about its place of origin outside our system. The fascinating thing is that all this can be inferred without physically approaching the object, only by measuring photons from a distance. When 3I Atlas was discovered, its initial brightness was faint and showed no evident signs of activity. This could mean several things: that it was too far from the Sun to activate its ices, that its surface was covered by a dark, deactivated layer, or that its composition contained very volatile ices that only react near the Sun. Over time, as its heliocentric distance decreased, its apparent magnitude began to slowly increase. This increase was measured at different observatories and compared with its distance from the Sun. After correcting the data, astronomers confirmed that the increase was not solely due to it being closer to us, but that the amount of ejected material was truly increasing. This confirmation marks the beginning of the study of its composition. When we talk about cometary composition, we mainly refer to two components: ices and dust. The ices can include water, H2O, carbon dioxide, CO2, carbon monoxide, CO, methane, CH4, ammonia, NH3, and other volatile organic compounds. Some sublimate far from the Sun. Others, like water ice, begin to sublimate closer as the object surpasses 2 or 3 astronomical units. The dust, on the other hand, is formed by silicates, complex organic compounds, and mineral grains mixed with ices. The relative amount of gas and dust released determines how the coma looks and how bright the object is. If there is a lot of gas and little dust, the coma is more transparent and less reflective. If there is a lot of dust, the coma becomes dense, reflects more sunlight, and increases the apparent magnitude. In the case of 3I Atlas, current data allow estimating that its activity is dominated primarily by the sublimation of volatile ices, which is typical for an object heating up for the first time after spending millions of years in interstellar space. The brightness has not increased explosively, but progressively, indicating the process is controlled by gradual solar heating. This suggests its surface is not covered by a thick layer of inactive dust, as occurs in comets that have passed multiple times near the Sun. Instead, it seems a considerable amount of pure ice is relatively exposed and responds quickly to the temperature increase. This fits the idea that this object had never before entered the solar system, or if it did, it was so long ago that it completely refroze. One of the most useful techniques for studying the composition of an object like this is spectroscopy. When the gas emitted by the coma interacts with solar radiation, some molecules absorb certain wavelengths and emit others. Each molecule has a kind of fingerprint in its spectrum. For example, the OH radical, which comes from the photodissociation of water, emits in the ultraviolet. Cyanogen, CN, has a very well-known band near 388 nanometers. Carbon monoxide and carbon dioxide show lines in the infrared. If telescopes detect these lines, one can infer which molecules are present in what quantity, and how their production varies over time. So far, some preliminary observations of 3I Atlas have reported weak signals compatible with water and fine dust, but more spectral data are still needed to fully confirm this. The increasing brightness also reveals the approximate size of the nucleus. Although this cannot be seen directly because it is enveloped in the coma, its diameter can be estimated using models that relate brightness, distance, and albedo. If the object shines more than expected for a small nucleus without activity, it means most of the light comes from the coma. But if its brightness is constant even without intense activity, it could indicate the nucleus is relatively large. Current calculations suggest the nucleus of 3I Atlas could be between a few hundred meters and a few kilometers in diameter, which is small compared to comets like Hale-Bopp, but similar to many interstellar rocks that might be wandering the galaxy. Another clue lies in the object's color. Cometary dust usually reflects more red light than blue, giving the coma a slightly yellowish or brownish tint. Measuring color indices, for example by comparing B and V filters, allows knowing if the dust contains more silicates, amorphous carbon, or complex organic molecules. Some interstellar comets like 2I/Borisov showed colors similar to comets from the outer solar system, which suggests planetary formation processes may be similar around other stars. If 3I Atlas shows different colors, it could mean its place of origin had different chemical conditions. Brightness can also indicate if there is fragmentation. If a sudden sharp increase in magnitude occurs followed by a drop, it could mean part of the nucleus broke and released gas and dust rapidly. So far, the brightness increase of 3I Atlas has been smooth and constant, indicating it has not fragmented, or if it did, it was not on a large scale. This is good for scientists because it allows studying its evolution without interruptions and without significant mass loss. When all these elements are put together, light curve, evidence of gas, estimated nucleus size, dust color, and coma stability, a coherent idea can be built. 3I Atlas is an icy object, probably interstellar, that is awakening due to the sun's heat. Its behavior coincides with what the physics of active comets predicts. There are no signs of technology, magnetic shields, or impossible accelerations. What there is ice turning into gas, dust scattering, and sunlight reflecting. And that, far from making it less interesting, makes it one of the best current opportunities to study how matter formed around another star behaves. When 3I Atlas reaches its perihelion, that is, its closest point to the Sun, its story will not end. On the contrary, it will begin the most delicate and least predictable phase of its entire trajectory. During the approach, the solar heat will continue to increase until it reaches its maximum at that point. And it is at that moment that astronomers expect to see the most marked changes in its brightness, its coma, its tail, and its physical structure. However, what happens immediately after perihelion is equally important. The object will begin to move away from the Sun, lose thermal energy, and show how a body behaves after being intensely heated, following millions of years in a frozen state. Understanding this stage allows for estimating how much material it has lost, whether it will survive as a single body or fragment, and how its activity will fade as it returns to interstellar space. After perihelion, the solar illumination will begin to slowly diminish. This does not mean that 3I Atlas will cool down immediately. Thermal inertia, the capacity of a material to retain heat, causes the nucleus to continue sublimating ices for a time, even when the radiation is no longer as intense. This effect creates a phase of delayed activity. Gases continue to escape, although with less intensity, and the coma remains present, but becomes more tenuous. In this stage, the brightness begins to decrease gradually. Astronomers will continue measuring its apparent magnitude and adjusting the models to understand how its light curve falls compared to the previous increasing stage. If the drop is smooth, it indicates the nucleus has preserved its integrity and continues releasing gas in a controlled manner. If the drop is abrupt, it could mean that a large part of the volatile material was depleted or that the nucleus fractured and lost mass rapidly. One of the most important questions scientists will try to answer is whether 3I Atlas will manage to survive intact after its passage near the Sun. Some comets like C/2012 S1 Ison disintegrated near perihelion due to extreme heat and gravitational stresses. Others like Neowise survived and continued active for weeks or months after. If the nucleus of 3I Atlas is small, porous, or composed of very fragile ice, there is a possibility it could break apart. But if it is compact and contains a more solid mixture of ice and dust, it could emerge whole. No one can know until it happens. Everything will depend on its real size, its rotation speed, the internal pressure of the gases, and the type of ices that compose it. Another crucial phase after perihelion will be the analysis of its trajectory. As the object loses mass and releases gas in non-symmetrical directions, it can experience small deviations in its orbit, known as non-gravitational forces. Astronomers will adjust their calculations to include these effects and see if the trajectory changes slightly after the passage. Although these deviations imply no danger for Earth, they are essential for understanding how the nucleus has been pushed by the gas jets. This allows for estimating the amount of mass lost, the main direction of activity, and how active the object remains as it moves away. The tail will also change near perihelion. The dust tail can become long and curved due to radiation pressure. The ionic tail can become more tenuous or disappear as the gas production decreases. As the object moves away, solar radiation will be less intense, the solar wind will have weaker effects, and the dust will cease to be pushed forcefully. Little by little, the tail will lose brightness, fragment, and finally disperse into space, leaving a trail of particles that will follow a similar orbit. This dust will slowly integrate into the interplanetary medium, although in this case it will not form meteor showers for Earth, since its trajectory does not cross ours. While this occurs, astronomers will also study if 3I Atlas shows what is known as residual activity, that is, if it continues sublimating materials even when it is far from the Sun, which could indicate the presence of ices more resistant to heat, like carbon monoxide. If this type of activity persists, scientists will be able to continue collecting data and comparing them with the phase before perihelion. This comparison will help determine if the composition of the nucleus is homogeneous or if there are internal layers with different compositions. The moving away will also reveal another key characteristic: the nucleus's rotation rate. Before perihelion, the rotation may have accelerated due to the gas jets. If it starts rotating too fast, it could break apart from centrifugal forces. After perihelion, if it remains intact, its brightness variations can be analyzed with precision and its rotation period estimated better. This will allow knowing if it gains speed during the passage or if it remains stable. Rotation is important because it determines how sunlight is distributed on its surface and how its activity evolves in future stages, should it ever pass by a star again. Finally, if it survives and escapes the solar system, 3I Atlas will return to interstellar space with less mass, with an altered surface, and with traces of its encounter with the Sun. It will have lost part of its surface ices and will likely be covered by a darker layer of heated dust. It will become a silent traveler that will continue its path through the galaxy, perhaps passing near another star millions of years from now. For us, it will be a unique visitor that left valuable data about what matter is like beyond our planetary neighborhood. In summary, after perihelion, the brightness will diminish, the coma will reduce, the tail will disperse, and the object will slowly cool down. The most likely outcome is that it will continue on its path out of the solar system, but every image, every brightness measurement, and every spectrum obtained in this stage will be key to understanding not only its present, but also its origin and its future. The passage of 3I Atlas through our solar system represents something much greater than a simple increase in brightness or a passing astronomical curiosity. This object, if officially confirmed as the third interstellar visitor discovered by humanity, becomes a unique opportunity to study matter that did not form in the vicinity of the Sun, but in another corner of the galaxy. Its scientific value lies not in mysterious theories nor in extraordinary speculations, but in the opposite: the possibility of applying physics, chemistry, spectroscopy, and orbital dynamics to a body that has traveled for millions or perhaps billions of years through interstellar space before crossing paths with us. Every photon reflected by its surface, every molecule released from its coma, and every grain of dust carried by solar radiation contains information about the processes of planetary formation beyond our neighborhood. Until now, the study of comets and asteroids from the solar system has allowed us to understand how the planets formed here, what materials existed in the protoplanetary cloud, and how minor bodies evolved over time. But this is only a local story. Objects like 1I/Oumuamua, 2I/Borisov, and now 3I Atlas open a completely different window: the possibility of directly studying fragments from the protoplanetary disk of another star. It is as if a piece of another planetary system had been thrown towards us and was now passing before our telescopes. We cannot touch it. We cannot send a spacecraft in time to intercept it, but we can still measure it, analyze its light, calculate its movements, and extract real and verifiable conclusions. That turns 3I Atlas into pure science, not fantasy. One of the first questions this object can help answer is whether interstellar comets are similar to ours or if they possess completely different compositions. If the spectra show similar proportions of water, cyanide, carbon monoxide, and dust, we could infer that planetary formation processes in other stars are similar. If, on the contrary, we detect rare compositions, different proportions of carbon or oxygen, or the absence of certain common compounds here, then it would mean that alternative paths exist in the chemistry of other solar systems. This information is invaluable for improving models of planet formation, protoplanetary disk evolution, and even theories about how elements are distributed in the galaxy. Another important aspect is its orbital dynamics. Its hyperbolic trajectory confirms it does not belong to the solar system. The velocity with which it arrived, the angle at which it enters, and the direction in which it leaves can be traced to estimate which region of the galaxy it comes from. One cannot pinpoint a specific star, but one can say if it comes from the galactic plane, from the direction of the Sun's motion around the galactic center, or from dense regions of interstellar space. This information helps understand how many interstellar objects could be traveling between the stars and how frequently we could detect them if we had more surveillance telescopes like the future Vera Rubin Observatory. 3I Atlas also serves to refine our technology and observation methods. To track such a faint and fast object, astronomers need sensitive cameras, well-calibrated telescopes, precise software for calculating ephemerides, and international collaboration networks. Every time an object like this is detected, these systems are tested. Coordination between observatories is improved, data is shared more quickly, and orbital models are adjusted with greater precision. In this sense, every interstellar visitor not only provides scientific data but also makes the way we observe the sky more efficient. But there is also a deeper meaning. 3I Atlas reminds us that the solar system is not isolated. We are in the middle of a galactic ocean full of fragments, dust, radiation, stars, and wandering objects. Some pass by unseen, others leave brief traces. This one, in particular, due to its growing brightness and activity, allows us to see it clearly. It reminds us that our star and our planets are not the center of anything but just one part of a gigantic structure, and that in that universe worlds are born, die, and throw out fragments that travel for eternities until briefly appearing in our telescopes. Furthermore, there is another question that sparks interest: whether these interstellar objects transport organic molecules, water, or materials that could be similar to those that gave origin to life on Earth. The theories of panspermia, which do not claim that life comes from outside, but that prebiotic molecules could have been transported by comets and asteroids, find a real example of transport between stars here. It does not mean that 3I Atlas could carry life, but that it can contain ingredients that, somewhere, under the right conditions, could participate in complex chemical processes. Again, this is not fiction but organic chemistry under real physical laws. Finally, the significance for the non-specialized public is different, but no less valuable. Seeing real news about an object arriving from another stellar system awakens genuine curiosity. If communicated well, without exaggerations, without lies, and without turning science into empty spectacle, it can inspire thousands of people to become interested in astronomy, physics, space exploration, and critical thinking. Objects like 3I Atlas are an educational and cultural opportunity. They can teach how science works. Observe, measure, compare, correct, verify, and accept only what the data allows one to affirm. For all these reasons, 3I Atlas does not need magnetic shields, nor impossible accelerations, nor extraordinary explanations. Its value lies in what it truly is: a piece of another stellar system that is being illuminated by our sun and seen by our eyes.